You know, when you see a rocket launch, you just see this incredible, steady column of fire. But what if I told you that inside that massive booster, there's a secret shake, a hidden vibration that engineers have been wrestling with for decades? Well, today, we're going to get into how they figured out this giant problem by, believe it or not, thinking really, really small. All right, let's just jump right in. What you're looking at here is a chart of the sheer, raw power from one of the space shuttle's solid rocket motors. You see that red line? That's the pressure inside the chamber. And the black dotted line? That's the thrust. We are talking about millions and millions of newtons of force here. I mean, enough to hurl a massive vehicle into orbit for 2 solid minutes. It's an unbelievable amount of controlled energy. But take a closer look at those lines. They aren't perfectly flat, are they? There's a little wiggle in there. Hidden inside all that immense power is a vibration, a kind of rhythmic pulse. Now, it might not look like much, but on a machine this complex and this powerful, any little unexpected shake is a huge deal. So what's causing it? What is this invisible force that's making this giant machine tremble? Okay, so to get to the bottom of this, we've got to go deep inside these massive motors. And I'm talking about the big ones, the engines that powered the space shuttle, the Ariane rockets, the Titan boosters. These are some of the most powerful launch systems humanity has ever built. And as it turns out, they all kind of share the same design. And yeah, the same hidden problem. So let's take a peek at the guts of one of these things. You might think it's just one giant solid piece of fuel, right? Nope. It's actually built in different segments, all stacked together. And right where they join up, you've got these things called thermal inhibitors. Now, their official job is to handle the insane heat, but let's just say they're a prime suspect in this little mystery of ours. Right, so this rhythmic shake, it's actually got a technical name. Pressure oscillation. Basically, it's this steady pulse, a low-frequency thumping in the pressure inside the motor. And that, of course, means the rocket's thrust is pulsing too. Now, don't get me wrong, these motors are built tough, they can handle it, but that oscillation, it's a potential weak spot, an instability that engineers absolutely have to get under control for safety. So, where is this shake coming from? It's not like a loose bolt or something. The real culprit is way more subtle. It's like this invisible dance of physics happening deep, deep inside the motor. The fancy term for it is aeroacoustic instability. And the main actor in this dance is something called vortex shedding. You've actually seen this a million times. Think about a flag flapping in the wind. As the wind blows past the flagpole, it creates these little swirls, these whirlpools of air called vortices, first on one side, then the other. That's what makes the flag flap. Well, inside a rocket, the fluid isn't air. It's super hot, screaming fast gas, and it's doing the exact same thing. And you can see here, it's not just happening in one spot. Those hot gases are swirling as they zip past those inhibitors we talked about. They're swirling right along the burning surface of the fuel. Heck, they even swirl when they go over sharp corners in the propellant grain. The inside of this motor is just this chaotic, incredibly complex, swirling mess of energy. Okay, now here's where it all comes together. This is the crucial part. Think of the rocket motor chamber like a giant organ pipe. It has its own natural sound, its own acoustic frequencies. So what happens when the rhythm of those swirling vortices, that vortex shedding, perfectly matches one of those natural frequencies? Bam! You get resonance. It's like pushing a kid on a swing at just the right moment. Those tiny little pressure pulses from the vortices suddenly get amplified into this huge, powerful, motor-wide shake. And that is our secret shake. So, knowing what's causing it is one thing, but how on earth do you study it? I mean, how do you test fixes for a problem that's happening inside one of the most powerful, most dangerous, and most expensive machines ever built? You can't just, light up a bunch of space shuttle boosters for practice. You've got to be smart. You've got to shrink the problem. I mean, let's really wrap our heads around this challenge. A space shuttle's solid rocket motor is over 38 meters long. That's like laying a 12-story building on its side. Firing just one of these things is a massive, multi-million-dollar event with a crazy amount of safety involved. So, yeah, testing it over and over, that is just not going to happen. Not an option. So, what's the solution? Well, it's actually beautiful in its simplicity. You build a perfect, tiny, scaled-down replica. A little lab-sized motor where everything, the shape, the materials, the physics, is an exact precise fraction of the real deal. And this table just shows you how wild the difference is. They made a 1:31 scale model. So the length goes from 38 meters all the way down to just over a meter. The burn time, which is 2 full minutes on the real thing, gets squeezed into less than 4 seconds. And the thrust, holy cow, it goes from over 15 million newtons down to a totally manageable 16 kilonewtons. It's literally a mini rocket designed to solve a mega problem. And just so you know, this isn't some one-off trick they used for the shuttle. It's a pretty standard practice. Here you can see the same idea being used for the European Ariane 5 rocket. On the left, you've got the massive, full-size chunk of propellant. And on the right, its little 1:15 scale model, used for the exact same reason, to test and figure out the physics without breaking the bank. All right, so the engineers went and built this amazing, tiny, intricate mini rocket. The whole theory was that if they got the scaling just right, that invisible dance of vortices would scale down perfectly too. But, that's all just theory. The real question, the multi-million-dollar question is, did it actually work? This is it. This is the moment of truth for the whole project. Could this little 4-second burn in a lab actually mimic the super complex physics happening inside a 38-meter-long monster? Because if it could, man, that would be a total game changer for designing safer rockets in the future. And here it is. This is the proof. Look at the graph on the left. That's real data from an actual full-scale space shuttle booster firing. You see that rhythmic wiggle, that up and down pulse? Okay, now look at the graph on the right. This is the data from their little 4-second model. I mean, come on. The shape of the curve, where the peaks and valleys are, it is a near perfect match. The mini rocket was singing the exact same tune as the giant. So, the verdict? A huge, undeniable success. The little mini rocket captured that secret shake perfectly. It proved the whole idea worked. It proved that you absolutely can study, predict, and, solve giant complex problems by thinking small. Okay, so what? What does this all mean? Beyond just this one cool experiment? Well, it has massive implications for how we're going to design and build the next generation of rockets. We're talking about making space travel safer, more reliable, and a whole lot more efficient. And the impact is, well, it's huge. This whole method gives engineers a quick, cheap way to test out new ideas. They can fiddle with the design of those inhibitors, change the shape of the fuel grain, and see what happens in a bunch of tiny, inexpensive tests instead of one gigantic, eye-wateringly expensive one. It lets them literally engineer these dangerous shakes out of the system, and that leads directly to safer, more trustworthy rockets for all our future missions. The researchers who did this work, they put it pretty modestly. They just said it was new in its kind and a step forward. But what they really did was create a powerful new tool for the toolbox. By figuring out how to scale not just the rocket's size, but the actual physics happening inside, they changed the game for building the rockets of tomorrow. So, figuring out this secret shake was a huge win for engineering, no doubt. But it really makes you think, doesn't it? As we get ready to build even bigger, even more powerful rockets to push out to Mars and who knows where else, what other hidden physics, what other invisible forces are still lurking out there, just waiting for the next generation of engineers to discover and to master?